Yeah.
Yeah, so it is my great pleasure to welcome Dr. Pranav Chaitanya Jayanti to our complex systems and dynamics seminar. It's always a great pleasure to welcome a former student. So Pranav actually has a dual degree from IIT Madras. Dual degree, right, Pranav?
Yes.
Correct.
Yeah.
And in fact, he was one of our students. So, uh, in the sense that long before complex systems and dynamics, Pranav was interested in complex systems. And he, in fact, did his dual degree project on the shell model of turbulence. And I think later on, he went to the University of Maryland College Park and proceeded on the analysis of models of superfluidity. I don't know how much turbulence is going to enter there. Uh, I've forgotten the name of your PhD guide, Pranav. Please
Oh,
repeat.
it's Konstantina Trivisa in the mathematics department.
So Pranav actually, his thesis is highly mathematical in nature, but he has a knack for explaining things simply. So I hope we will all be able to understand it.
Yeah.
We have had we have many people speaking from many angles in this complex systems and dynamics course, and I think, but the number of speakers who have spoken from the mathematical point of view has actually been quite small. So it is a great pleasure to have somebody who's, and in fact, going to present the mathematical aspects to us. And okay, I hope I will not ask the kind of questions which you used to get asked, which is that how is this related to pipe flow? But maybe it's a relevant question. So let's see. There are other people present. If any of them feel that it is related to pipe flow and want to ask how is it related to pipe flow on Pranav's behalf, please do. Please do. So it was Pranav has always kept in touch over the last all the time that he has been away, which is a real pleasure. It's really nice when people go away, but they don't forget about IIT. And he's anyway been on this campus since birth, Pranav.
Almost, yes.
Almost, yes. So we were just talking this morning about how pleased your parents must be that you are back in a totally different capacity. It is not just your parents. We are your teachers, Sayan and we are also very happy that you are back at a totally different level and a totally different capacity. And we hope maybe it would be very nice if we could see it in a still higher capacity at a somewhat later date. But let's not go into all that now. Let's start. So over to you, Pranav.
Okay.
Sayan, would you like to add anything?
No, I think it's nice to see Pranav. That's all. I mean, and his smiling face. So yeah, please go ahead. Yeah.
Okay. Firstly, I want to thank Professor Nilima Gupta and Professor Sayan Gupta for their invitation and to chalk out all the logistics for presenting here. It is definitely a great pleasure to present at IIT Madras, where I studied and which has set the foundations for my career. So it's really nice to come back. Um, yeah, I'm going to be talking about various models of superfluidity and some mathematical aspects of them. Uh, the work presented here, the mathematical work presented here was done during my PhD, and it was all done in collaboration with my advisor Konstantina Trivisa in the math department at the University of Maryland College Park. Okay, I think we need to first set the stage for what superfluidity is and try to explain some of the physics before we get into any of the mathematical details. So we know that most regular fluids are described very well by the incompressible Navier-Stokes equations, at least in certain flow speeds and yeah, but in general everyday life. The Navier-Stokes equations are used to model fluids with constant density, right? When we make the assumption that the shear stresses are linearly proportional to the shear strain rates, then we get what are called Newtonian fluids. And this is exhibited as viscosity, what we call viscosity on the large scales, but which is essentially the particles of the constituent particles of the fluid colliding with each other and exchanging momentum with each other in order to achieve equilibrium, right? That is what viscosity is microscopically, but on the large scales, we see it as just a drag force. Now, certain fluids are fundamentally inviscid. They're called superfluids. Okay? And for this, one would expect, therefore, that if they have no viscosity, then all the particles must move in unison, so together in one state, so to speak. And this is actually achieved and seen in the ground state of Bose-Einstein condensates, okay, which is a quantum mechanical phase transition. So examples of superfluids are helium-4 and helium-3. This is a bosonic superfluid. This is a fermionic superfluid. And because they have some very cool properties, like the presence of a critical velocity, and they exhibit film flow and another phenomenon known as fountain pressure, which we will not get into right now, but if I have time, I'll describe them later on. Here is a phase diagram of helium-4, the helium-4, the bosonic isotope. So we know that for any substance, right, if we cool it isobarically at a constant pressure, so in this picture along a horizontal line, if we reduce the temperature, it's going to go from being a liquid into a solid phase. And that's what happens here in helium-4 as well. However, if the pressure is below about 25 bars, right, then it goes from one liquid state to another liquid state. And this is known as the superfluid state. Okay. And this transition happens roughly around 2.17 Kelvin, and that's known as the lambda point or the lambda temperature. So at or above 2.17 Kelvin, you have completely regular helium liquid. It's called the normal fluid. At 0 Kelvin, you have completely superfluid. It's all of it is superfluid. So between 0 and 2.17, there's a mixture, and it keeps, as you keep cooling from 2.17 all the way down to 0, the fraction of superfluid keeps increasing, and the fraction of the normal fluid keeps decreasing. So the particles of the normal fluid basically condense down into the ground state of this Bose-Einstein condensate kind of phenomenon, okay? And that becomes the superfluid. So because we have two fluids, the famous physicist Landau came up with something known as the two-fluid model to describe this system. So he said there is a normal fluid and a superfluid, denoted by the subscripts N and S. They have their own densities and velocities. The normal fluid is interpreted as a collection of thermal excitations of the superfluid phase. And the normal fluid carries all of the thermal energy and the entropy. The superfluid does not carry any entropy, and it exhibits frictionless flow. This, the theory and the predictions of Landau's two-fluid model were first established experimentally, were verified by Andrew Nikashvili in a beautiful experiment where he set a pile of disks, one on top of the other, and started to rotate them in this helium fluid. And he kept varying the temperature. And it turns out that you can actually get a correlation between so these disks, as they rotate, they would dampen because of viscosity of the surrounding fluid. This damping rate and the period of their oscillations, that could be related to the viscosity of the fluid. So as you change the temperature and more, as you keep cooling it down and you get more superfluid, the overall viscosity of the fluid reduces. And so that can be observed in the damping rate. And so that proved that there were actually two fluids and one of them was converting into the other. Now, when you consider these two fluids, they both react the same way to a mechanical stimulus, which means if you apply a pressure gradient, then the pressure gradient drives both the fluids in the same direction, from high to low pressure. But if you apply a thermal gradient, they move in opposite directions. The normal fluid goes from high temperature to low temperature, as you would expect for any fluid, whereas the superfluid would go in the other way. So it moves towards higher temperature. this is one of the more curious properties of superfluids. Just to explain a little more of the physics of superfluidity, I think it's nice to see one of its directions of application, which is turbulence, right? And this is actually all I'm going to talk about turbulence. It's going to be very brief. We know that in regular classical fluids, we have Kolmogorov's theory, which works pretty well up to certain approximations, which is derived by using some basic assumptions of isotropy and homogeneity of the turbulence, and we assume that there also exists an inertial range. And based on these assumptions, one can derive the Kolmogorov spectrum, the famous k to the minus 5/3 power law for the energy spectrum, and also a formula for the Kolmogorov dissipation scale. And below this Kolmogorov scale, so for length scales smaller than this, viscosity homogenizes the flow. Right? So this is the general picture of classical turbulence. There have been a lot of studies on quantum turbulence too. So it's important to recognize that in superfluids and quantum fluids, the vorticity is quantized. It can't take just about any value one pleases. It can only take certain discrete values. And the vorticity is localized to what are called topological defects. I will explain this a little further in a minute. So Feynman visualized quantum turbulence to be, or quantum flows to be basically a tangle of interacting quantized vortices. Okay, so you have a bunch of vortex filaments that are just interacting with each other, and they're completely tangled with each other. Okay. This is unlike the continuous distribution of vorticity that we have in classical turbulence. Now, in classical turbulence, we know that there is this famous Richardson cascade where energy goes from large length scales to small length scales, or low frequencies to high frequencies, through interactions, nonlinear interactions between various eddies, and the eddies keep breaking up and energy cascades down. So in quantum flows, we have similar cascade, but we actually have two of them. So one is this regular cascade that happens by the nonlinear interactions at the largest length scales. The other is basically interactions of Kelvin waves, okay? So which occur along the vortex filaments. So in quantum fluids, the vortex cores are topologically constrained, which means that they act like solid bodies. The filaments act like solid bodies. They can't change in size, and they move along the fluid like solid particles. They don't diffuse or get bigger or smaller. And there are no direct viscous losses as well. Now, like I said, energy is transmitted to larger frequencies, or wave numbers here, k, via reconnections between various vortices. So anytime two vortices reconnect with each other, then this can trigger some Kelvin waves along the filament structure. So if this is the vortex, then there'll be a wave that goes like that along the filament and propagates along it. And these waves can interact with each other non-linearly. And this nonlinear interaction unlocks higher wave numbers, and eventually the wave numbers or frequencies get so large that phonons are emitted, and a dissipation occurs through the boundaries of the system. Of course, when you're at non-zero temperatures, like we saw earlier, there's a mixture of both the fluids, and the normal fluid is constantly dissipating via viscosity, the normal helium. So here is a schematic of the energy cascade. So this is our integral length scale, or the length scale, or the wave number associated with the largest dimension, or the dimension of the box in which the whole system is, the fluid is. Okay. And L is the length scale which characterizes the intervortex separation distance, the average intervortex separation distance. KL is the corresponding wave number. So between KD and KL, we have an inertial range with the power law, minus 5/3 power law, right? This is because of regular fluid eddy-eddy interactions, right? And then there's usually a bottleneck that's observed. And beyond this, we actually don't have experimental observations, but some theoretical models predict that there should be another power law scaling of minus 5/3. Although this is, there's not 100% consensus on the exponent here. It could be minus 5/3, or it could be minus 7/5. which are pretty close to each other, but the literature is generally leaning towards a -5/3 spectrum here too. And this is because of the Kelvin wave cascade. And eventually, the phononic dissipation has a k to the -1 spectrum, which happens beyond this, around here. Okay. So the transition to the superfluid state is a second order phase transition. And to describe this, we generally use an order parameter psi, which is a complex function. And because it's a complex field, you can write it as a magnitude f times e to the I times a phase factor phi. Okay. Now, we know that in quantum mechanics, by the way, this order parameter is essentially like a multi-particle wave function. It's the wave function of all the particles together that form the condensate. Okay. So if you take this wave function and take the absolute value square, you get some kind of probability density, right? And so if you multiply that probability density by the mass of the helium atom, then you get a mass density, a superfluid mass density, okay? And using basic quantum mechanical analogies, we can also define a quantum mechanical mass current, whose expression looks like this. This is very familiar to anyone who's studied some quantum mechanics before, to the physics community in general. So once we have this mass current or momentum, and we have the density, we can then define the velocity to be the mass current divided by the density. And when we do this, we get an expression for the superfluid velocity, which clearly is a gradient flow, right? It's a potential flow because it's the gradient of a scalar field. And this means that this field is irrotational, right? US is irrotational. But US itself can only be defined whenever the density or F is non-zero. If F is 0, we can't divide here by the density and get this expression. So like I said, US is a potential flow. So it's irrotational everywhere in the domain except at regions where F is 0. And those are the places where you have the vortex filaments. And those are called the topological defects. Now, when we impose the condition that the wave function psi has, or the order parameter has to be single valued when you go around the loop, then we get the quantization condition for the circulation. So the circulation around a vortex filament has to be quantized, some integer times the Planck's constant divided by the mass of the helium atom. Now, all the above, Schrodinger picture, all of this that I just discussed is valid and it's a pretty decent approximation of what happens at 0 Kelvin, where there's pure superfluid, because we can plug in the order parameter of the wave function into the nonlinear Schrodinger equation, NLS, and then solve it to solve the dynamics of the problem of the system. But at non-zero temperatures, when T is greater than 0 Kelvin, we know that there's a mixture of both the fluids, right? And that means, and it's also known from experiments that the two fluids interact with each other. The two phases interact with each other. So we have to characterize this interaction, which is typically a retarding interaction. Apart from academic interest, this also has practical interest to engineers because helium is used very often as a cryogen. It's also used as a solvent in some spectroscopic analysis methods. And there are some cool applications of gyroscopes, very, very sensitive gyroscopes that have been built and designed using superfluid helium. Okay. So we have to come up with these interaction models that describe the interaction between the super and normal fluids, right? Depending on the length scale, there are 3 main different classes of models. So if you're considering the dynamics of the problem at length scales that are much larger than the intervortex separation distance and approximately the size of the domain itself, then you would have macro scale models, which are basically classical Navier-Stokes based models. If you have and then there are mesoscale models where the length scales of interest are roughly the intervortex separation. For these, we have these vortex interaction models, which I will not get into here. I'm going to discuss the macro scale and micro scale models in this talk. So when we go to much smaller length scales than the intervortex separation, so roughly the the length scales are of the order or a few times that of the vortex core sizes. Then we have microscale models. So these use some kind of nonlinear Schrodinger description of the superfluid. Okay. So like I said, I'm going to be talking of one macro scale model and one microscale model. So let's get started with the large scale picture. So at the very large length scales, we can ignore the fact that these vortices are discrete and they have a quantized circulation. We assume that everything is nice and smooth, so to speak. We basically get rid of the quantum mechanics from the system, and we assume both fluids are classical, and we can describe the interaction between them using a coupling, a nonlinear coupling term that is empirically motivated. This gives rise to a system of equations called the Hall-Winen-Bekarovich-Kalatnikov equations, or HVBK for short. Okay. These have been used to very well to describe systems where you have a high density of well-aligned vortex filaments, like in 2 dimensions, or if you're trying to study Taylor-Couette flow, superfluid Taylor-Couette flow, which is basically this the situation when you have 2 cylinders, one inside the other, and 2 concentric cylinders, and there's fluid in the annular region between the 2 cylinders. And one of the cylinders is typically the inside one, I believe, is made to rotate while the outside one is kept stationary. And this causes, at high enough rotation speeds, this causes some instabilities. So the HVBK equations have been used to study this kind of superfluid Taylor-Couette flow. They've also been used in the simulation of quantum turbulence. This is the model that we consider. Okay, let me just give you a quick rundown of the various equations. So here is, so again, N and S are the subscripts for normal and superfluid. So this is the incompressibility condition for the normal fluid and the superfluid. Whoops, sorry. This is the momentum equation for the normal fluid, right? The normal fluid viscosity, and then you have a coupling term that couples to the superfluid. The superfluid momentum equation, we added a viscosity here, which may be curious. I'll get to that in a minute. And then you have again, the nonlinear coupling. The coupling itself is, like I said, nonlinear and depends on the superfluid vorticity, because whenever the superfluid vorticity is 0, so away from these topological defects, it's been observed that the 2 fluids don't interact with each other. They only feel the presence of each other when there is a non-zero superfluid vorticity. And at this point, I must also point out, make it clear that we are not talking of the regular multi-phase flow that is very commonly encountered in engineering, where in chemical engineering and in aerospace engineering, for instance, where we have 2 different phases of fluids with a strict boundary between them. Both of these phases, normal and superfluids, they both occupy the entire domain, and it's just that some of the particles behave like a superfluid and some of them behave like a normal fluid, and they only interact where the superfluid vorticity is non-zero. Okay. The viscosity for the superfluid, like I said, is just an artifact of the because we need to handle high frequencies. If this isn't there, then there is no control over, we have no control of the higher frequencies that arise due to the nonlinear interactions. So we've added this, and this is typically added even in numerical simulations of these models. Okay, so because we have our system already set up, let me just mention quickly the main result we've derived, or we have arrived at for this system. We were able to show global well-posedness for this system. Okay, what that means is when you have a partial differential equation, well-posedness requires 3 things: existence of solutions, uniqueness of solutions, and continuous dependence on the initial conditions. Which means if you change your initial conditions by a little bit, then the solution also changes by a little bit. It doesn't change by a lot. Okay, so what we have here. This is a lot of technical details, but I want to draw your attention to the segments in red. So we've shown that there exist unique, strong solutions to the system, and that the solution map is Lipschitz continuous, which means that basically that if the last condition in well-posedness. Okay, and the word global here means that the solutions exist and all of these properties exist for an infinite amount of time. Okay, I'm going to give a quick sketch of the proof so that people in the audience can understand what are the main ingredients here. So we use standard Navier-Stokes equations theory, okay, but we have to obviously deal with the coupling term. And the idea of the proof is as follows. We set up a map, okay, P capital phi sub T, okay, such that this map phi solves the heat equation, right? This is basically the this part alone is the heat equation with a perturbation, and the perturbation is all of the nonlinearity in the problem. And we define a certain function space. Okay, the details, what it is exactly, is not really relevant right now. We define a function space such that our solution, we seek solutions in this function space, and then we show that this map is a contraction map. Okay, what does that mean? So we notice here that if you fix US, okay, let's assume US is some fixed function. And if you plug in some value for UN, then you get a value, you can solve this equation and find out what phi or this capital phi is, right? So phi depends on this field UN. So when we want to show that it's a contraction map, what we want to do is, if you take a ball in this space, in this function space xn, okay, the ball has a radius rn. And if you take a velocity un inside this ball, then when you substitute un here and calculate the value of phi, that value of phi is once again within this ball. So, okay, so any value un, its map phi remains within this ball of size r. Next, we want to show it's a contraction. That means if you take two values, un1 and un2, which are inside the ball, and apply this map phi to both of them, then the values of the map will be closer than the original values un1 and un2. Okay, so what this means is, therefore, if you take some value un here, put it here, and then calculate phi, and take that as your next value, next input for un, plug that back in, and get another value for phi, plug that back in, and keep iterating this procedure over and over again, then because of these two properties, that they remain inside the ball and that they keep getting closer, that sequence that you get for phi actually keeps getting close enough that they will eventually converge when you do an infinite number of such iterations. And that converged, the convergent value in the end is the solution to the original equation. So that's how you prove the existence of solutions. Okay. We repeat the same thing for the US system, setting up a similar perturbed heat equation for the superfluid equations. Okay, and we do something known as the bootstrapping argument to get solutions that are local in time. So essentially, by the end of this whole process, we will have proven that there exist unique solutions to the system that will exist up to some time t star. We don't know what we don't know if t star is infinity, but we have some finite time t star. Okay. Now, in order to extend this to an infinite amount of time, what we need to show is, no matter how long we consider the system to be, it is never going to leave this ball. It will forever stay inside this ball. Okay? And to do that, we use perhaps the most used inequality in mathematical analysis, called the Grönwall's inequality. Okay? Take a look at this system. You have some function x, dx by dt is less than or equal to some function k times x. Now, obviously, you can solve this using just regular integration and show that x of t is bounded by this exponential bound, right? The initial value of x times an exponential bound, as long as k is integrable in time, right? Now, it turns out you don't need only a linear growth rate here for dx by dt. It suffices that even if you have a logarithmic correction factor, you can still show that x of t will be bounded for any time, up to any time capital T, with what is a double exponential bound. So x to the x of 0 to the power of e to the power of this. So it's a double exponential bound. Okay. So because we have this, what and why am I discussing this? So we derive something known as a higher order energy estimate, okay, for the system. Basically, we seek solutions in some kind of some function space, right, which is denoted HM. So we set up an inequality of this form, or well, actually of this form initially, right? Because you have d dt of some norm of the normal velocity and the super velocity is less than the normal velocity and the super velocity times some huge quantity here. This huge quantity is like your k of t. So as long as we show that k of t is integrable in time, so you can integrate this in time, then we can show that this quantity can be bounded, just as shown here. The problem is this itself is not directly integrable in time. It's difficult to show that. So we make use of a very nice estimate, a potential theory estimate from fluid dynamics, which can bound the gradient of velocity in L infinity, which is the maximum value of gradient of velocity in the whole domain. We can bound that with the L2 norm, the square integrable norm of the vorticity, and the L infinity, or the maximum norm of the vorticity. So once we have this, this gives a logarithmic correction factor, right? Because you again have u in that function space norm. And because we have a logarithmic correction factor which does not affect the exponential growth, we can once again show that this quantity, which is the HM norm, which is a certain function space, we can show that this, the velocity is finite. It remains within the ball. And for all time t, for any time t, as long as this quantity is integrable. And so that allows us to take our local solution and say, okay, since our solution is, we know it exists up to t star, but even which t star, by the way, was the previous time here, but because it exists within the ball, even beyond t star, we can keep extending the solution and it will stay all the way up to infinity. It will be finite. Okay, so that's how we show that we have a global solution. So we were able to show global well-posedness for this PDE, and there are a lot of other questions that can crop up with the system of HVBK equations. Probably the most important one is the fact that we added a viscosity coefficient, right? So we have the superfluid viscosity being non-zero. Now, this is done in numerical simulations, like I said, because we need to handle these high frequencies. But even from an abstract mathematical analysis point of view, like the one shown here, I strongly believe that the system is ill-posed. So the system will immediately break down if we do not have viscosity for the superfluid because of the nature of the coupling. So this is a very important question to be explored in the future, but and it obviously also holds important ramifications for numerical simulations of the system. And of course, what we have considered here is the two-dimensional version of the HVBK equations. The 3D system is a monster. It has very difficult to handle terms that describe the bending of vortex filaments and the forces associated with that. And it's nasty, to put it lightly. And I don't know if it's possible to even do any analysis for it right now at the current state of affairs. Right. So this is some basic overview of the results we have for the macro scale model. And with this, I want to switch gears and move into a microscale model. But before that, I want to just pause and ask if there are any questions. Anybody has any questions or comments?
I have a question.
Yes.
Has anybody done a renormalization group for this? Because basically, in your function space, you are converging to a fixed point. Am I right?
Yes.
Huh? Right?
Yes.
Yeah. And somehow your viscosity is crucial for this. Without that, you don't think you will converge, at least.
Yes, without viscosity, we won't have a handle on some of these terms. So when we are trying to establish inequalities of this form, we won't have sufficiently good handling of these terms if we don't have viscosity.
Right. So it actually it forces you towards the fixed point, right? Somehow in the function space. In the function space.
But yes, I think you could say that, yes,
I could
because
say
the
that,
norm
right?
we consider does have the viscous coefficient, the
Yeah.
norm in which we're considering the contraction. So that does have the viscous coefficient. So yes.
Has anybody done the RG for this, the renomination group?
That's a good question. I've never specifically looked for that, but I've not come across it. That's all that's the best
Okay,
I can
because
say.
it looks like it should work here. It's
Right. Yeah.
right. I mean, now
Yeah.
that you have this result, clearly it should work.
Right. Yeah. That would be very interesting. I've not come across an RG analysis of this before.
Of this. Okay, I
In
won't
fact,
hold you up. Yeah, go on.
there has been no rigorous analysis of any of the superfluid models in mathematics literature. Either the HVBK or the next Pitevsky model that I'm going to discuss, there has been no rigorous mathematical analysis. But if you're asking from a physics perspective, from a physicist perspective, perhaps it might have been there, but I've never seen it.
Okay, it's worth having a look, but I won't
Yeah.
hold you up. Please go to the next one.
Okay. Yeah. So next, we're going to switch gears and move to a microscale model. Like I had showed in the sketch before, this uses some kind of nonlinear Schrodinger picture for the superfluid. So here we have what's known as the Pitevsky model that was derived by Lev Pitevsky all the way back in 1959. So this is actually a slightly simplified version of it. So we have the nonlinear Schrodinger equation here that describes the order parameter of the superfluid, psi. Okay. We have what is known as the incompressible inhomogeneous Navier-Stokes to describe the normal fluid. Incompressible because it's divergence-free velocity, but the density can change from point to point. So it is inhomogeneous in that sense. So, so we have the density equation, the continuity equation. We have the divergence-free equation for the velocity, and we have the momentum equation for, well, the momentum rho times u. Now, the operator B is the coupling operator that couples the NLS, the nonlinear Schrodinger, to the Navier-Stokes, as you can see here through the B operator. For those in the audience who've done quantum mechanics before, you will recognize that this here looks like the momentum operator. Minus I h bar gradient is the momentum operator, right? We've set h bar to be 1, so minus I gradient is really the superfluid momentum. M times u is the regular classical momentum, right? We also set m to be 1. So this is the normal fluid's momentum. So what we have here is the difference in momenta of the super and normal fluids. So you square this difference and then divide it by 2 times m again being 1. So this is the relative kinetic energy of the two fluids, okay? And this is just a self-interaction of the superfluid with itself. So the coupling basically seeks to reduce differences in the kinetic energy or the momenta of the two fluids. Okay? And so I'm going to discuss some of the features of this, but before we jump to any of those, we have to, a partial differential equation is only complete once you set up its boundary conditions. So let's do that. Firstly, we're going to work in a smooth bounded domain in 3 dimensions, okay? 3D smooth bounded domain. So you can think of it to be like a sphere. Okay? Now on the boundary, we impose the requirement that the velocity and its derivative vanish. And on the boundary, we again impose the conditions that the wave function and its first 3 derivatives vanish. Okay. Now, any fluid dynamicists in this audience may wonder, if we have a Laplacian here, how are we imposing 2 boundary conditions for the velocity? Or if we have a Laplacian here, how are we imposing 4 boundary conditions for the wave function? This I will discuss shortly, but and I will also justify why we need these extra boundary conditions. They come from a technical result that we use, a technical mathematical result. but we have figured out a way to impose the boundary condition. So let's discuss some features of the model. It's obviously a non-linearly coupled NLS NSE system, like I just discussed. The coupling is like relative kinetic energy. Most importantly, the coupling allows for a bidirectional mass and momentum transfer, okay, because the coupling exists both in the mass equation and the momentum equation. Okay. The continuity equation has a sign indefinite source term. This is by far the biggest problem or roadblock we had during the analysis of this system. Normally, we have the continuity equation with a 0 on the right-hand side. But here we have this term because there can be a transition of one fluid into the other. And so that can cause a change in the density, which means you must have a source or a sink term. The only problem is this is sign indefinite. It's not always positive or always negative. If you integrate it over the entire domain, then it is non-negative. But at any given point of the domain, we don't know if it's positive or negative. Okay? So yes, we've assumed divergence-free velocity and cubic self-interactions because of this. This is cubic here, right? We could have assumed anything else differently. It really wouldn't make a difference to the analysis as we've done it here. We've assumed divergence free to simplify the original model a little bit, because otherwise, again, the full Pitevsky model is very, very complicated and sophisticated. Okay, and of course, like I said, we have the extra boundary conditions, which I will justify shortly. So we seek weak solutions to the system. We always have to specify what kind of solutions. So we seek weak solutions. We end up with stronger solutions, but we set out seeking weak solutions. What is weak? So when we say weak solutions, we take the system of equations that we have, we multiply them by these test functions, okay? A complex field phi, a divergence-free real field phi, and a real scalar field sigma. So we multiply each of those, the NLS, the density equation, and the momentum equation by these functions, which are nice and smooth. And then we integrate by parts, okay? So that the derivatives move away from the from psi, u, and rho, and move onto these test functions. And we demand that we are looking for solutions that satisfy the governing equations in the sense of, in this integral sense. Okay, so you notice the time derivative has moved from the wave function onto the test function, from the momentum onto the test function, from the density onto the test function, and so on. So we transfer some of these derivatives in this sense. So we're looking for a weaker class of solutions that need not be very smooth. Okay, right. So we seek such a triplet psi, u, and rho, which is a weak solution to the Pitevsky model, where our initial conditions are in certain function spaces, which I want to briefly describe. So our initial wave function is in the space h0 5/2 plus delta. What this means is take the 2.5 plus a little bit. So delta is between 0 and a half. Okay, let's call it 0.1. So 2.5 plus 0.1, 2.6. You take the 2.6th derivative of this wave function, the initial wave function, and that derivative is square integrable. Okay, the 0 here basically imposes the boundary conditions. Similarly, the velocity has 1.5 plus a little bit, that many derivatives that are square integrable. The d here imposes the boundary conditions and the fact that it's divergence free. And the initial density is just bounded. Okay? It's in L infinity. Okay, so those are our initial conditions. These are the function spaces that we'll be working with. I just want to briefly mention that there have been works done for the nonlinear Schrodinger equation with some extra potential terms, non-local potential, because these have been used to model dipolar quantum gases. And in fact, there's a nice hydrodynamic perspective to the Schrodinger equation also, where you recall that you can write the complex wave function as a magnitude times e to the I phase factor. So if you use that formulation of the wave function, you can actually extract out a mass balance equation and a momentum balance equation from the nonlinear Schrodinger equations. And that gives you a formulation known as quantum hydrodynamics, QHD. And there has been quite a bit of mathematical analysis done on this system. And it's also used quite a bit in physics formulations of quantum mechanics. Okay, I'm going to skip the rest of it. It's basically some literature review of the inhomogeneous incompressible Navier-Stokes. Now, to the best of our knowledge, that's what this acronym is. This is the first investigation of a bidirectionally coupled NLS-NSE model. In the literature, there has been some attempt to analyze a similar coupled NLS-NSE model, but that was unidirectionally coupled, where the Navier-Stokes was affecting the Schrodinger equation, but not the other way around. Okay, and that made it much simpler to analyze. Right. So now we consider slightly more, our initial conditions are slightly smoother than what is usually considered for weak solutions in the Navier-Stokes. Okay, because we have to deal with this fact that the density has a source term. Normally, there is no source term in the density, but we have a source term, and so that poses a lot of problems. And that also dictates our use of these higher order boundary conditions, which in turn dictate our choice of the basis functions we use for a Semi-Galerkin scheme that we set up, which I'm going to describe now. So first, here is the result, and I'm going to walk the audience through this. So we fix a delta between 0 and a half. Like I said, could be 0.1, could be 0.2. And we take our initial conditions, psi 0, u 0, right, in these function spaces with sufficiently, there's a sufficient number of derivatives that are square integrable. We suppose that the initial density is bounded both below and above throughout the domain, right? This means nowhere in the domain is the density 0 initially. Then we can show that there exists a time t and a weak solution to the system, okay? And in fact, the solutions we find are turn out to be strong, that is, they're sufficiently smooth in the wave function and velocity to be called almost strong solutions. In the density, they're still weak. They don't have enough regularity. Okay, they satisfy the density equation in that integral sense that I showed before. And you have an energy balance that is satisfied by this solution. Psi, u, and rho, the triplet satisfies this energy equation. Okay, so quickly let's go through the strategy of proof here to show the existence of these solutions. Like I said, the density is not purely transported because of the nagging source term that we have. So what we do is we can look at the Lagrangian coordinates of the flow. So you choose a particle, right, initially in the flow, and then move along with it as the flow progresses. And you can write the density, the solution for the density equation along this path as the initial density plus the change due to the source term. Now, we don't want the density to become 0 at any point in the fluid. So what we say is, because the initial density starts off with a minimum value small m, we are going to stop this simulation in quotes once the density at any point in the domain reaches some value epsilon. Okay. So for this, because this is bounded below by small m, and if you want this to be bounded by epsilon, it is sufficient that this quantity is bounded by above by m minus epsilon. Or in other words, it is even more sufficient if the absolute value of this integrand is integrated and is less than m minus epsilon. And even further, it is sufficient, not necessary, but further sufficient, that if you use the Cauchy-Schwarz inequality, you can split this time integral as a square integrable here, like an L infinity on this and L2 on this. Okay, that's what we have here. And this quantity is less than m minus epsilon. So we seek to find solutions which satisfy this inequality. Now, what is done generally in the mathematical literature is to first derive these estimates. So we assume that there exist solutions. We derive a priori estimates on those supposed solutions. We construct approximate solutions that satisfy these estimates using approximate equations. And then we pass to the limit in the approximation. So just like the contraction mapping argument that we discussed earlier, we show that these approximate solutions, as we, let's say it is indexed by some index n, as n goes to infinity, the approximations keep getting closer and closer and will eventually converge onto some function. That function is the final solution that we are looking for. Okay. Right. Now, remember, we need this quantity B psi to be bounded, right, in L infinity, which is basically the maximum value of it should be finite in the domain. In 3 dimensions, there is this nice mathematical result that the L infinity norm of a function is less than the h3 halves plus delta norm. Okay, so a little better than 1.5 derivatives is enough to bound this. And in order to derive such a bound of this partial fractional derivatives, what we do is we take the nonlinear Schrodinger equation, multiply it throughout by minus Laplacian, which is basically 2 derivatives to a sufficiently high fractional power. And then we derive for this quantity, minus Laplacian to the power s times psi. This quantity, we derive an energy estimate. So we want this squared integrated over space. So when we do that, we end up with some integration by parts, right? And in order to get rid of the boundary terms on those integration by parts, and because s is actually pretty high, the order of the derivative is pretty high, we need a lot of the derivatives to vanish on the boundary, especially in this term. And that's what gives rise to these extra boundary conditions for the wave function. Okay, I hope that this overview makes sense. Similarly, if we want to bound B psi in this function space, remember that B had a U square in it. So if B contains U square, if to bound B, we need to be able to bound U also in this function space. And in order to do this, we use a technical result in analysis called the Leo-Magin lemma, which requires that the velocity and its time derivative are in dual function spaces. So the velocity we choose to be in some space h0s, where 0 means that it vanishes on the boundary, and the time derivative is in h minus s. Now, because we need u to be in h 3 halves plus a little bit, s has to be greater than 3 halves. And if the velocity is in h0 3 halves plus a little, then both its value and its derivative need to necessarily vanish on the boundary. Okay? So that is the reason for imposing the extra boundary condition for the velocity as well. Okay? I hope this clarifies the boundary conditions, or at least the need for them. Now we'll see how we actually impose those boundary conditions. So we consider this differential equation, right? Let's say V is some velocity field, not the same as U, some velocity field. Solving this equation, this partial differential equation, minus Laplacian square V plus gradient of a pressure field P is equal to F, and V is divergence free, which means the pressure P is essentially a Lagrange multiplier that allows you to impose this condition, the divergence free condition, and V satisfies both of these boundary conditions. So we can actually show that if you project this equation onto the subspace of functions which are divergence free, that's called the Leray projector. We eliminate the pressure term, okay? And this equation reduces to the projector times minus Laplacian square V is equal to F. This operator here, Leray projector minus Laplacian square, we call the by-Stokes operator. It's very similar to the Stokes operator that is encountered in fluid dynamics all the time. We can show that this operator actually has a set of divergence-free eigenvectors which satisfy these boundary conditions, and they're orthonormal in L2 and orthogonal in H2. So we use these eigenvectors A sub j to form a finite linear combination, okay, with time-dependent coefficients. And this finite dimensional linear combination becomes our approximate velocity field. And notice that because these functions satisfy the boundary conditions, so will the approximate velocity fields. Okay, we do a similar thing for the wave function. We find a PDE that is sufficient, that has sufficiently high number of vanishing derivatives, and then we use the eigenfunctions of this operator, which satisfy all these boundary conditions, and form a finite dimensional linear combination, and that gives us an approximate wave function. We then write down approximate equations, right, for the whole system. Plug these approximations, right, these approximations here, because they have time-dependent coefficients which are unknown. We plug those into the system here and show that that system has a set of solutions. But all of this is done assuming that n is some finite value, okay? And in the end, we show that even when n goes to infinity, these solutions that we derive actually converge. And that convergent value is the convergent function becomes our final solution, psi, u, and rho. Okay, so that's how we show the existence of solutions to the Pitevsky model. Okay, right. And yeah, once we show that solutions exist, the next question is whether they are unique. Okay, but those are just the last few slides. And before that, I want to again pause and see if there are any questions about what's been said about the Pitevsky model so far, or any comments. Okay, in that case, I'll move on to the uniqueness. So now, generally, the way we prove uniqueness is essentially setting up a Grönwall's inequality. You remember the inequality from before, where we had dx by dt is less than k times x, where x is the difference between the solution. So we assume that there are two solutions that start from the same initial conditions. And then we look at the difference of the solutions and prove that that difference is bounded by, or the rate of change of that difference, dx by dt, is bounded by k times x. And because x is 0 initially, because both the solutions start from the same initial condition, they will continue to remain, the difference will continue to remain 0, because the rate of growth of the difference is bounded linearly. So if they are 0 initially, then they will continue, the difference is 0, it will continue to be 0. Okay. Now the problem is when you consider weak solutions, they don't have enough smoothness in order to justify all of the calculations that we do to set up that Grönwall's inequality. So what mathematicians settle for usually is something called a weak strong uniqueness. So instead of saying the weak solutions are unique, which we cannot, we say, okay, if there is a strong solution that starts from the same initial conditions as the weak solutions, then the weak and strong solutions are equal. They're the same. Okay? So that's what weak strong uniqueness is. So we don't claim that there exists a strong solution. We just say that if there is one such solution, then the weak and strong solutions are unique. Now, the usual weak-strong uniqueness argument doesn't seem to work for our system here. I'm going to briefly describe that before introducing another notion called weak moderate uniqueness. Okay. So here is the usual statement of a weak-strong uniqueness. So let's say we have really weak solutions, so much weaker than what we constructed in the previous section. Okay. So truly weak solutions for the wave function, velocity, and density. Then if you have a set of strong solutions, psi tilde, u tilde, rho tilde, that start from the same initial data, such that, and by strong, I mean that they have the same regularity as the weak solutions, plus this additional regularity, okay, where W13 is a function space, which means the first derivative of the density field is cube integrable. Cubic integrable, it's in L3. And here the first derivative of the velocity field is bounded. And the first time derivative of the velocity field is also bounded. Okay. So this requires a lot of smoothness on these strong solutions. So if the strong solutions, which are very smooth, if there exists such a strong solution from the same initial data as the weak solutions, then the solutions are identical. Okay, that's the general statement of a weak strong uniqueness theorem. The problem here is that this doesn't work because because of the coupling terms that we have in the continuity equation, the mass equation, and the momentum equation. So we can't handle some of the calculations and estimates required for this. So instead, we have to modify some of the notions of solutions given here. Okay. So what we had earlier, what we constructed in the previous section was a solution that was strong in the wave function. That is, it was nice and smooth in the wave function, strong in the velocity, nice and smooth in the velocity, and weak in the density. So it's not smooth in the density. That's what we constructed before. In the previous slide, what I was alluding to as the usual weak, strong uniqueness result, we considered very weak solutions, okay? And we tried to establish weak, strong uniqueness for the case where the solutions are very strong. And this does not seem to work, right? So what we can do, however, is we look at a set of solutions that that have smoothness between this and this. So they're weaker than the solutions that we constructed, but not as weak as really weak solutions. So let's call them less weak solutions, for lack of a better name. And then we look at moderate solutions which have smoothness between this and this. And we can actually show that there is a less weak moderate uniqueness result. So once again, if we take some initial data and show that there exists some less weak solutions and a moderate solution that also exists from the same data, then the two of them are the same. This solution and this solution are identical. Okay. So what we've essentially done is we've increased the regularity of the weak solution, and to balance it out, we've been able to decrease the regularity of the strong solution and come up with the moderate solutions, and shown that these are unique with respect to each other. Okay, and that's what is shown in this theorem here, the statement of this theorem. So we've increased our weak solution to be less weak by increasing the derivative order from H1 to H2 and from H0 to H1. So one derivative better, right, for the wave function and velocity. But instead of a strong solution, we have a moderate solution, right? The density of the moderate solution is the same as before, but the velocity, you don't need that its spatial derivative is bounded. And you don't need that its time derivative is bounded. It only has to be integrable, cube integrable. Then we can show that these solutions are identical, that the moderate solutions we have here and these less weak solutions are identical. So the main feature here is we've only been able to construct these solutions. We don't know if these exist or if these exist. But if in the future someone has the ability to prove or construct the existence of these solutions and these solutions, then we already have a uniqueness result for them. So assuming that such solutions exist, we have already shown that they would be unique. Okay. So so that's our main uniqueness result that we have for the system. And now the exploration of this Pitevsky model has led to various other directions being made known to us. So for instance, it would be very nice to see if anybody can extend these results to being global solutions. As I discussed before, we need the density to be non-zero everywhere in the domain. So we have to stop this simulation of the PDEs as soon as the density reaches some value epsilon somewhere in the domain. And that leads to local in time solutions. We have not been able to show that the density will always remain bounded below by a positive value. If that is possible, then we can actually try to show global in time solutions that exist for an infinite amount of time. That would be very nice. That would be a nice extension of this work if it's possible. And of course, we've added these extra boundary conditions, which are mathematical artifacts of the analysis methods that we've used, and it would be obviously better to do without these extra conditions. So again, that's an open question. If we can modify the analysis arguments in order to not require them. And looking at the complete Pitevsky model is, again, like in the HVBK case, this is going to be a very, very complicated and ambitious task. And maybe someone might be ambitious enough to look at it. I also want to mention that there are no simulations done of the Pitevsky model itself completely. So there have only been simulations. Let me go back here. There have only been simulations done for this equation, assuming that the velocity u is given. So we assume some kind of velocity field that is known and plug that in here and only simulate this. There have been no simulations done for the entire system because it's just numerically just prohibitive. The computational cost is too high. So yeah. So with that, I am done with my presentation, and here are some references I used. So if there are any more questions or comments or discussion, I'd be happy to address them.
I have a question regarding your extra boundary conditions. as engineers and people trained in physics, perhaps we normally associate a boundary condition with some physical conditions. So when you say extra boundary condition, does it mean a new physical law or new something, some new physics that you're talking about, or is something hidden there?
No, like I mentioned, the boundary conditions are only a mathematical artifact here. We've needed to use them because we require require to be in certain function spaces. We have not been able to figure out a way to mathematically analyze the system otherwise. So the basic idea here is that normally when you do a Galerkin scheme, we expand the solution in terms of some finite dimensional approximation. So we use a finite dimensional set of basis functions which satisfy these boundary conditions. So as long as we start with an initial velocity that has extra boundary condition that satisfies the boundary conditions, then we will continue to remain in that function space which satisfy the boundary conditions, and that can be shown mathematically. So there is no new physics here by adding the condition, the BCs, but it's a mathematical necessity.
Thank you.
I also want to add that we will not require this in one dimension. If we were to analyze the system in one dimension, we won't need this for the velocity. That actually comes from this part here. So we've needed to bound this factor, the upper bound. We need an upper bound for B psi. In 3 dimensions, this is bounded by this function in the Sobolev space, h3 halves plus delta. In 1 dimension, this can be bounded by h1 half plus delta. Okay, generally in D dimensions, it's hd by 2 plus delta. So in 1 dimension, you won't need such high derivatives in this whole expansion here that you won't get the extra boundary terms, and so you won't have to deal with the extra conditions. In 2 and 3 dimensions, you do need this.
Pranav,
Yes.
can you comment on the initial condition dependence of these results, or at least, or maybe of the numerical results? See, numerical results would be highly initial condition dependent, isn't it?
Yes.
But once you do this, it would not be, right? Or is it? Mathematically.
So for the for the HVBK equations, we've shown well-posedness of that system of PDEs. So there we show that this solution map is Lipschitz continuous. So which means that if you change the initial conditions by, let's say, some value delta. So if you have 2 initial conditions, U1 and U2, and U1 minus U2 is less than delta, then the final velocities, let's say V1 and V2, once you simulate it for a certain amount of time, then V1 minus V2 is bounded by some constant times delta. So if delta is very small, then so the solutions will also continue to remain within some bound. So there cannot be this exponential chaotic divergence of trajectories because the HVBK is well posed. We don't have a similar thing for the Pitevsky model. We have only constructed we've only shown the existence of solutions. We have not been able to show the this Lipschitz continuity with respect to the initial data. But in general, if you look at the coupling term here, this has a heat. This gives some kind of heat equation nature to the whole equation. It gives a diffusive. It renders the equation a little bit diffusive because we know the Schrodinger equation is a dispersive equation from here, but it becomes diffusive because of this. And so one would expect that the system would be well behaved in that sense because it's diffusive, but that's not guaranteed. Obviously, I mean we still don't know. For instance, the usual Navier-Stokes problem is still an open problem. That is diffusive. It has the viscosity, but we still don't know if global solutions exist and things like that. So, and numerical evidence has pointed to some certain initial conditions in Navier-Stokes leading to possibly singularity formations. So we can't really comment on it unless there is mathematical proof.
Okay.
But yeah, it would be nice to see this system being the whole system being numerically simulated. That would be nice to see. It's never been done before.
I see. No other questions? Anybody?
Just a comment, presentation was excellent. Okay.
Thank you.
Yeah. And of course, I did not understand many things, but did learn a little bit about superfluidity. Okay.
Thank you.
Thank you.
Yeah, that was the aim. So thank you. The superfluidity and these models are well known in physics, but I don't think it has been of that.
So I knew only application of helium was to fill the balloons.
Okay.
Okay.
I should probably include that in my first slide then. Although I don't think inhaling superfluid helium is good for us.
But gyroscope application was really something that I probably would want to look into. Thank you.
Oh yes, yeah. There are, like I said, some nice applications of superfluid helium. I mentioned something about a gyroscope. That's actually a very nice application where you have like a ring, like a donut-shaped object, which has superfluid filled inside it, and you pinch one segment of the ring. So one segment is narrowed and looks kind of like a venturi, and this whole setup is very carefully maintained, so that if there is any rotation of the gyroscope, then the superfluid will flow through that pinched region, and that would actually cause some sonic emissions. And you can calibrate the frequency of the sound that comes out of it to the amount of rotation that you've made. So, and it's extremely precise. So people, I think, have built a proof of concept of this already. It's a really cool device.
Okay, thank you.
Yeah, the reason you need superfluid is because the pinch is so narrow that normal helium won't flow through it. It's too viscous to flow through the pinch. So.
Just one question. I actually missed some part of this presentation, but as I followed, it was wonderful presentation. Just I saw that you were talking about helium, right? So are there any other, substance that you can mention which will reach that, superfluid state?
Yeah. So like I said, superfluidity is essentially a Bose-Einstein condensation phenomenon. So the most commonly studied superfluid is helium-4, but there are other fluids, other Bose-Einstein condensates, like sodium atoms have been shown to exist in a inviscid Bose-Einstein condensate phase. I think lithium atoms also have been shown to exhibit that behavior. And there are some other theories, it's not been experimentally verified yet, but theories of neutron stars having an inviscid superfluid phase inside them at very low temperatures and high pressures.
But the temperature range, what you are talking about here, near zero and all, it will be very different for them, right?
Yeah. Depending on the on the substance, the temperature varies. So, for instance, for helium-4, like I mentioned before, that the transition, this happens around 2.17 Kelvin, right? Around 2 Kelvin, because it's bosonic. For helium-3, it actually happens 1,000 times lower at 2 millikelvin, because helium-3 is a fermionic substance. It has a spin half, and Bose-Einstein condensation necessarily requires bosons. So what happens is when you cool it down all the way to 2 millikelvin, just like in superconductivity, electrons Cooper pair up, right, to each other like that. The helium-3 fermions pair up, and that pair then becomes a boson.
Okay.
and then that can condense. But you need very, very low temperatures before the atoms are sufficiently at rest that they can actually pair up. Otherwise, they're moving around too fast.
And do we need to worry about the any special equation of state for this kind of fluids, or are they following the ideal equations?
So I believe that the regular Bose-Einstein condensation derivation assumes that the bosons are a very dilute gas. So that's how the original BEC derivation of the condensate state was done. But for in helium-4, these are strongly correlated liquids because they're liquid moving into a superfluid phase. They're still very strongly correlated. So you do have to include, modify the original BEC theory, but it has been done. I don't know the details, but you have to make sure that you factor in the liquidity of the substance, and it's not a dilute gas anymore.
I mean, it's a mixture. You're saying it's a liquid plus gas type of. It's a mixture.
It's not a gas. It's there's a normal liquid, and there's a superfluid, which is a liquid. It's very strongly correlated. It's not a gas.
But the equation of state would be, similarly applicable for both.
I don't know about. I can't comment on a classical equation of state if that's what you're asking. PV equals nRT kind of thing. I don't know what the classical equation of state would be for this.
Yeah, no, because there are some special equations of state when they convert to different types of situation. For example, the supercritical state, and as opposed to the normal state. So that's why I asked. Yeah.
Okay. Yeah, I don't know about any classical equations of state for this.
Okay. Yeah. Thank you.
Yeah.
Yes. So maybe maybe we should.
Yeah, I mean, that it was a very nice talk. Thanks, Pranav. It's not that I didn't understand much of it, but it was very nice.
Okay,
it would have been better if you could have a physical seminar so that the interactions could have been better. But unfortunately, I could not get the necessary things done.
Yeah, that's okay. It's not a problem. But thank you. This was still a nice, definitely a nice opportunity for me to present some of the work. So thank you very much for inviting me.
Oh, you are here this week, right?
Yes.
Yeah. So just drop by sometime so we can at least see you physically.